So in this case, we have two areas. We have AI, and we have A2, and we have three parts of our wall. We have, I'll call this part 1, part 2, and part 3. We can then take the we can calculate the shear stress is within each of these three walls. So for wall 1, we have Q1 is going to be equal to tau 1 times T1. All right. So we know that we can say that tau at wall 1 would be equal to Q1 divided by T1. For wall 2, it'd be very similar. There's only one shear flow, which you say is Q2. And that would be equal to tau 2 times T2. So again, tau 2 equal to Q2 over T2. And then the last one we have is wall 3. All right, in wall 3, we're gonna have we can define the net shear flow, which I'll call Q3, would be equal to, let's say, we can say that Q1 is going to will be positive, and we're going to say that Q3 or Q2 would be negative. Okay, so because they're going to be going in opposite directions, so I should redraw that. So we can say Q1 is going this way, Q2 is going this way. So in wall 3, they're going to be going in a smaller, or going against one another. So we had to subtract them from each other. So if you do that, we end up getting the difference between those shear flows has to be equal to the shear stress in that section times the thickness of that section. So if we rearrange that, we get the shear stress is equal to Q1 minus Q2 over T3. So is there any question about how you can calculate the shear stress within a cell if you know the shear flow is within each of the cells and the thicknesses? Okay. Okay, good. Then the next part would be if we have a externally applied torque. Okay. We're gonna on the last page we defined these two sets of equations. Okay, for the overall torque applied to the system and the angle of twist theta. So we're going to just define those for this situation here. So our overall torque T is going to be equal to 2 times the sum of our area times QI. All right. So we have two cells here. So it's just going to be equal to 2 times A1 times Q1 plus A2 times Q2. Right. So that's our first equation, right? The only unknowns are Q1 and Q2. Okay. So our second equation is that the second set of equations we have to develop is for the angle of twist in each cell. So we have two cells. So for cell 1, you define phi as being equal to 1 plus V L over E A1, and we integrate from Q T of S ds. Okay, so so this integral here, you would get one. So everything out in front is a constant. All right, and then this integral on the right hand side, we'd have to break into two parts. The first part would be on the let's see here, be on the outside section of our tube here. So that would be the shear flow over that part of the tube would be equal to Q1, and I'm going to call that length um, uh, and I call it so the shear flow is constant along that length, along that part of the section, and the thickness along that part of the section is also constant. So I'll call that T1. All right, so then this integral here, these terms can come out, and then it's just going to be the integral of ds. So I'm going to call the length of that wall 1, as being equal to S1. Okay. And then the second part, the remaining part of the cell, is along the inside of the wall, or goes along the inner part of the tube, and that's going to be the shear flow over that part of the tube would be equal to Q1 minus Q2, which is the net shear flow over that region, divided by T3 times S3. Where S3 is just the length of that section. All right. So are there any questions about that part of completing that integral for this section? So, L would be the length of the tube. So if this tube is attached to a wall, the length, this should be the length. Okay. So yeah, so the question was the sides of what the S terms represent, and the S terms represent the length of the sides of the part of the section that we're going over. So the first part of the integral is over the curved part of left hand side of the tube, and then the second term is for the center section of the tube that connects the top and bottom regions. Good. Thank you for the clarification. All right, so we now have to repeat this process for cell 2, so it should be pretty similar. All right, so for cell 2, we're gonna get so it's the same coefficient, so it's the same equation. All right, so use the second area instead, and then it'd be the same integral. All right. So again, these are all constants, so we can just keep them out in front. All right, and then we're given so then for the right hand side, we're gonna use let's see. We're look at the curved tube, and in that part of the tube, the shear flow is equal to Q2, the thickness is equal to T2, and the length we'll call S2. Okay. Then within the other part of our section, the black part of our section, or the center part of the section here, all right, what we're going to do here is we're going to have Q2 minus Q1 over T3 S3. So what you're going to do when you're making these equations, it's important that the shear flow within the cell that you're evaluating should be positive. Anything that's going in the other cell that's opposing it, and like you should always refer to the diagram when you're doing this, but if the shear flow is opposing the direction of the cell that you're evaluating, that would be negative, okay? So don't write Q1 minus Q2 down here, you would get the incorrect answer, okay? So I understand that these are the same net value, but the sign does matter, okay? All right. So what you end up with here is you have 3 equations, all right, and you have 3 unknown terms, okay? The 3 unknowns are Q1, Q2, and phi, or theta, okay? So what you could do is you could rearrange these equations, and so you could solve the first equation in terms of Q1 or Q2, and then you could plug that into the other 2 equations, and then you could put theta in terms of Q1 or Q2, and then you could solve the last one, okay? So you can see that these problems would get relatively tedious pretty quickly. So typically what you could do is everything else in the equation you know. So you can oftentimes you can write these in terms of, you could write an equation where you'd have Q1, Q2, and theta. And then you could have a coefficient matrix here, and then you can have all your known constants over here. This would be, in this case, it would be a 3x3 matrix. And then you could take the inverse of this 3x3 matrix and multiply it by the other side to find Q1, Q2, and theta.